we will be discussing the architecture and application of array processors. As we push the boundaries of scientific computing, standard processors often struggle with massive amounts of data. Array processors were designed specifically to solve this problem by changing how we handle numerical arrays and matrices. Over the next 10 minutes, we will explore what they are, the two main types, their advantages, and their limitations. Let's start with the definition. An array processor is a computer or processor with a specific architecture designed for dealing with numerical arrays, such as matrices. Unlike a standard CPU that handles various tasks, this is a specialist. There are generally two ways these are built. First, it can be created as a self-contained unit that connects to a central computer via an I/O port or internal bus. 2. Alternatively, it can be built as a distributed array processor. In this setup, the processing units are distributed across and closely linked to a section of the computer's memory. Essentially, it is about moving the processing power closer to the data structure it needs to manipulate. Broadly speaking, array processors can be divided into two distinct categories. 1. Attached array processors. 2. SIMD array processors, which stands for single instruction stream, multiple data stream. We will now look at each of these in detail to understand how they differ. First, let's look at the attached array processor. Think of this as a turbocharger for your computer. It is an auxiliary processor connected to a general-purpose computer specifically to enhance and improve the machine's performance in numerical computational tasks. It achieves this excellent performance by using numerous functional units to perform parallel processing. Structurally, the attached array processor includes a common processor with an input-output interface and a local memory interface. Crucially, the main memory of the host and the local memory of the array processor are linked, allowing data to flow between them. Please focus on the diagram. On the left side, we have the general-purpose computer, which acts as the host. It communicates through an input-output interface. On the right side, we have the attached array processor. Notice the connection at the bottom. There is a high-speed memory-to-memory bus. This bus connects the main memory of the host computer directly to the local memory of the array processor. This architecture allows the general computer to offload complex math tasks to the array processor, which performs the work in its local memory and sends the results back via that high-speed bus. Now, let's move to the second type, the SIMD array processor. SIMD refers to the organization of a single computer with multiple parallel processors. Here is the key concept: the processing units are designed to work together under the supervision of a single control unit. This results in a single instruction stream, one command, being applied to multiple data streams, many data points, simultaneously. As mentioned in the slide, it comprises several identical processing elements, PEs, each with its own local memory, ALU, and registers. The master control unit is the brain. It controls the actions of all processing elements, decodes the instructions, and determines execution. The program is stored in the main memory, and the control unit retrieves the instructions. When a vector instruction is received, it is sent to all PEs simultaneously, and the results are stored in memory. A famous historical example of this is the ILIAC 4 computer, manufactured by Burroughs Corporation. However, it is important to note that these are highly specialized computers. They are excellent for numerical issues stated as vectors or matrices, but they are not suitable for general-purpose computations. If you look at the diagram, you will see the master control unit at the top. This is the single brain of the system. Below it, you see multiple vertical lines connecting to PE1, P2, all the way to PEN. These are the processing elements. Attached to each PE is its own local memory block, labeled M1 M2, through Mn. The data flows from the main memory into these local memories. The master control unit shouts one command, like add 5. And PE1 adds 5 to its data, P2 adds 5 to its data, and so on, all at the exact same instant. So, why do we use these systems? Simply put, array processors enhance the total speed of instruction processing. The design optimizes performance specifically for repetitive arithmetic operations. This makes them significantly faster at vector arithmetic than a standard host CPU. Another benefit is independence. Since most array processors run asynchronously from the host CPU, the system's overall capacity is improved. The host can do one thing while the array processor crunches numbers. Additionally, because array processors have their own local memory, they provide extra memory to systems that might otherwise be limited. This architecture is critical in specific high-tech fields. Array processing is used in radar and sonar systems, where signal processing must happen in real time. Anti-jamming technology. Seismic exploration for oil and gas. Wireless communication. Medical applications, such as MRI or CT scan processing. Speech enhancement and astronomy applications. While these processors are extremely useful for problems requiring high parallelism, they come with a catch. They require a change in programming methodology. You cannot just take a standard sequential program and run it here. Converting conventional programs to support array processors is complex, and you often need to design entirely new parallel algorithms to match this approach. Let's assume we have adapted our code. What are the specific advantages? The first is massive data parallelism. Array processors are built for number crunching. Here is why it works. Imagine you need to brighten every pixel in an image. That is 1,000 identical calculations. A sequential processor does them one by one. An array processor can do all 1,000 in a single clock cycle if it has enough PEs. This offers orders of magnitude speedups over sequential SISD processors for vector and matrix operations. The second advantage is hardware efficiency, also known as the silicon budget. In a standard multi-core CPU, MIMD, every single core needs its own complex control unit to fetch and decode instructions. That takes up a lot of physical space on the chip. In an array processor, there is only one control unit for the entire array. This saves silicon space and power. Manufacturers can pack more actual calculation units, ALUs, onto the chip because they don't have to waste space on duplicate control logic. However, we must be realistic about the limitations. First, there is the branching penalty. Array processors hate if-else statements. Since all PEs must execute the exact same instruction, you cannot have half the processors do option A while the others do option B. They have to take turns, which cuts performance in half. Second, there is algorithmic rigidity. These are not general-purpose machines. If your algorithm is sequential, where step B depends on the result of step A, an array processor is practically useless. They also struggle with complex data alignment. Data must be stored in contiguous vectors. If your data is scattered, like in sparse matrices, the processor wastes time just trying to gather it. Finally, we face issues with synchronization and scalability. Array processors require tight, microsecond-level synchronization. Trying to coordinate this across a network, distributed system is inefficient because the fast PEs constantly have to wait for the network's go signal. Regarding scalability bottlenecks, while you can add more PEs, the single control unit eventually becomes overwhelmed by the signal delay to the farthest PEs. Unlike clusters which scale easily, array processors have a hard hardware limit. In conclusion, array processors represent a powerful but specialized tool in computer architecture. They offer unmatched speed for vector and matrix problems through massive parallelism and hardware efficiency, provided we can overcome the challenges of programming rigidity and data alignment. Thank you for your attention.